Welcome back, everyone. I'm going to continue from where I left off on Monday. On Monday, we were talking about decision theory, specifically a method called risk minimization for making decisions in a classifier. Today we're going to apply it to a specific case, namely the case where both of your classes have normal distributions. So you have points in class C, points not in class C. The class C points are in some normal distribution, and the points that are not in class C also come from a normal distribution, but a different one. So that's our fundamental assumption, is that each class comes from a normal distribution. Which is sometimes also called a Gaussian distribution. And the way we write a random variable x that comes from a normal distribution is like this. X tilde n for normal distribution with parameters mu, the mean, and sigma squared, the variance. And it has the following PDF. By the way, I'm going to do, hopefully in some previous statistics class, you've seen the univariate normal distribution and the multivariate normal distribution. The one on the right is sort of halfway in between. It's going to be multivariate, meaning that x is a vector, but the variance is going to be the same in every direction. Next week, we'll talk about the most general version of the multivariate normal distribution, where the variance is different in different directions. But for today, it's going to be isotropic, which means the variance is the same in every direction. And when you do it that way, it's almost as simple as the univariate normal distribution, but you might notice a slight change. Or two. All right, so that's the PDF of our normal distribution that we're going to use today. And to be clear, mu and x are both vectors. So this could be a PDF over a multidimensional feature space. But the variance is a scalar. We'll change that next week. All right, so here's what we're going to do. We want to apply risk minimization that I talked about on Monday. So the first thing we need to do is we need to actually estimate the parameters of these distributions, so we know what is f for the set of points in class C, and we know what is f for the set of points not in class C. So to figure that out, we need to estimate these parameters twice, once for class C and once for all the other points. And in fact, we could have more than two classes. So let's say that for every class, C, we estimate the mean, mu C, for that class, the variance sigma squared subscript c. And we also, as you'll recall from Monday, need to know the prior probability on each class. Remember what percentage of people have cancer, what percentage don't have cancer. That's called the prior probability. And we're going to use the common notation pi to refer to a prior probability. That's used a lot in statistics, and we're going to use it too. So pi subscript c is the probability that if you just choose a random sample point, that it will turn out to be in class C. All right, so suppose that we can estimate these parameters, and now we know the normal distribution for class C, and now we know the normal distribution for all the other points. Then, now we can apply the principle from Monday to figure out what is the Bayes decision rule. Well, okay, we can't actually know the true Bayes decision rule unless we truly know the exact classes, but if we can approximate the distribution of the classes, then we can approximate the Bayes decision rule. Now the Bayes decision rule predicts the class C that maximizes the posterior probability. Remember, that's one of the things I asked you to memorize on Monday. We pick the class that maximizes the posterior probability at point X, if X is our test data that we want to classify. Maximizing the posterior probability is equivalent to maximizing this thing. We know that from Bayes' theorem. So we just apply this rule. We know F, having estimated the parameters. We know pi, because we estimated that as well. And we just, now if someone gives us a test point X and asks our classifier to classify it, you just compute this value for class C. And then you also compute the corresponding value for class not C. And you decide which of those two numbers is bigger. That's the one that wins. That's our classification. Now, when you're doing this, we're not entirely happy with this exponential here for several reasons. It makes the expression complicated. It makes it slow to compute. Computing a bunch of exponentials on your computer is kind of slow. So what we're actually going to do is do a little transformation on this expression to replace it with one that's easier to compute, because you don't have to do an exponential on every point. And the way we're going to do that is, first of all, we're going to observe the fact that the logarithm of a scalar value omega is a monotonically increasing function for all positive values of omega. So maximizing this thing here is equivalent to maximizing something else that's going to come out a little simpler. And the something simpler, I'm going to give it a name. I'm going to call it the function Q. And there's going to be a different function Q for each class C. It's going to take a test point X, and it's going to be the logarithm, the natural logarithm, of this thing here multiplied by a constant just to make it even simpler. And so the constant in question is root of 2 pi to the power of d. And we have the PDF for class C at the point X, and we have the prior for class C, all in there. So again, what I'm doing is I'm just taking this function that I want to maximize. I want to find the c that maximizes that, and I'm putting it here. It's the same thing. And what we get when we do that is we get an expression which, well, what's important here is that this expression is quadratic in x. It's not exponential in x. All right, so what I've done here is I've taken this PDF here, the PDF for the normal distribution, and I've plugged it in here as f for class C of x. And then when you work this out, this falls right out. And again, I want to repeat that what makes this special is that it's quadratic in x, and so kind of simple as a function of x. No exponentials involved. Now, there are a few logarithms. You might ask me, aren't logarithms just as expensive to compute as exponentials? Well, yeah, but those are constants. You only have to compute the logarithm of each constant once, and you're done. Whereas this exponential, you would have to compute it for every test point, every training point. So we want to avoid that. So I called this function q to remind you that it's quadratic. And again, just a reminder that this is the normal PDF. Which estimates how likely it is that we'll pick sample point x if we just pick a random item in class C. All right, so one more time, what I'm going to do is I'm going to compute this quadratic function for each class. If I have, and this works if I have more than 2 classes. So if I have 5 classes, I can have 5 of these quadratic functions, one for each of the 5 classes. And then when someone gives me a test point x, I compute all 5 of those quadratic functions at the point x. And I look at those 5 numbers that pop out, and I look at which one is biggest. That's the winner. That's the class that my classifier will return. Because that's what Bayes' theorem says is the most likely class. One more thing I want to mention is the fact that if you want to add an asymmetrical loss function to this, you can. The place where the loss function would go is here with the pi of c. So wherever you see a pi of c, you can like replace it with pi of c times the loss function. Any questions about that so far? All right, so Gaussian discriminant analysis is actually an overarching term for at least 2 different algorithms. One is called quadratic discriminant analysis, also known as QDA. The other one is called linear discriminant analysis, also known as LDA. They're pretty similar. We'll start with QDA. It comes more naturally, I think. Now, for the moment, let us suppose there's only 2 classes. I'll call them class C and class D. Then, what is the Bayes optimal classifier? Well, if you knew the true distributions, then you had the true exact values of QC and QD, then you would always pick C if the function QC is greater than the function QD at the point X that we're currently trying to evaluate. Otherwise, we would output class D. So again, what we're doing here is we're just picking the class with the bigger posterior probability. But instead of computing the posterior probability in full, I have this thing which is simpler to compute because it's quadratic. And so by comparing those two quadratic values, I get exactly the same answer I would get if I actually compared the posterior probabilities. But still, the principle is pick the class with the biggest posterior probability. I want you to notice in particular that this is now essentially the decision function of this classifier. So this is another example of a classifier that computes a decision function to classify new points. And it's a quadratic decision function. That is quadratic in X, the test point, which is what matters. And so the decision boundary, specifically the Bayes decision boundary, because this is the Bayes classifier, is the set of all points where QC minus QD equals 0. Now, if you only have one feature, if we're working in a one-dimensional feature space, then the Bayes decision boundary might have 1 or 2 points, because that's a polynomial with typically 1 or 2 roots. But when you go to higher dimensions, the Bayes decision boundary is something else, which is called a conic section in 2D. In general, it's called a quadric. I discussed quadrics before in lecture 4 when I talked about using quadratic features. Same thing comes up here. And reminder from the end of last lecture that here's an example of what they might look like. So these are, again, 2 different views of the same 2 functions. And so it might be, for instance, that this blue curve here is the that the blue curve is the Gaussian that approximates the points in class C. So essentially, this is the normal for class C. And then the red curve is the normal distribution for class D, the other class. And the feature space is, well, here's one feature. Here's the second feature. Vertical direction is the PDFs. On the right-hand side, we've got the exact same functions again. Here's the two features, x1 and x2 are now the horizontal and vertical axes. And we have a contour plot to show us the two PDFs. And so again, here's the blue PDF, here's the red PDF. And the decision boundary, as I pointed out last time, you can see the decision boundary here is where the red meets the blue. And on the right-hand side, you can see the decision boundary is this white curve here separating the two different kinds of isocontours. So this is an example of what you might actually get from doing QDA. The decision boundary you get, and anytime you have a test point and you want to classify it, well, if it's in the blue region, you classify it as Class C. If it's in the red region, you classify it as Class D. Now, this is two classes, but as I said, QDA works very naturally with more than two classes, as many as you want, really. So here's what the figure might look like if you do QDA with a bunch of classes and look at their decision boundaries. So the black points here are the center of each distribution, of each Gaussian. And together, these Gaussians set up decision boundaries, which are curvy but meet each other in places where they fork out, when there's three or more distributions meeting at a single point. So for those of you who've heard of Voronoi diagrams, you might notice this looks a little bit like a Voronoi diagram. In fact, it is a special kind of Voronoi diagram called a multiplicatively additively weighted Voronoi diagram. Any questions about that? All right. So what I've explained so far is how do you write a classifier that, given certain normal distributions for the class and for the different classes, chooses how to classify a test point. You might not be satisfied with just a classification. You might also, I actually want to know the probability. Don't just tell me it's in Class C, tell me the probability that it's in Class C. So in other words, I want the posterior probabilities. Well, fortunately, this method makes it pretty easy to get the posterior probabilities. So let's take a look at how we can get those, what the simplest formulae are for them, and then let's look at some graphs so that we can get a feeling for what those posterior probabilities look like. It's easiest in the two-class case, again. So let's assume we've just got two classes, C and D. And we're going to apply Bayes' theorem to find that the probability of a specific point X being in Class C is, well, here's Bayes' theorem. Let's look at the PDF for Class C times the prior probability of Class C. And we're going to divide this by the sum of the same thing over all the classes. So by Bayes' theorem, that's the posterior probability that we want. All right, so what I want to do is I want to take this expression and relate it back to QC. And you might recall that QC was defined here. And this is the expression that in particular, that I want to pull out and say, how does that relate to QC? Well, another way to rewrite that formula that I just spotlighted is we can move the logarithm to the other side of the equation where it becomes an exponential. So now we have e to the power of QC is root of 2 pi to the power of d times the PDF for class C times the prior for class C. Again, this is just the definition of QC rewritten. So what I'm going to do now is I'm going to take this and substitute back in something that's a function of QC. And when I do that, I get the probability that I'm in class C for a particular point, little x, is e to the power of QC over e to the power of QC plus e to the power of QD. So that looks maybe simpler, maybe not than what we had before, depending on your point of view. What I'm going to do now is I'm going to simplify slightly more by dividing both the numerator and the denominator by the numerator. Divide both top and bottom by e to the QC, and the top just becomes 1, and the bottom becomes 1 plus e to the power of QD minus QC. Now at this point, you might recognize that this QD minus QC is basically just my decision function, minus my decision function to be precise. But this is the same decision function we used before with a minus sign. So what I'm going to do is I'm going to express that expression kind of in two parts. First, I'll compute the decision function, and then I'll apply a little scalar transformation to the decision function. So I will write it as some function s applied to the decision function QC minus QD and what is that function s? That's right, sigmoid, also called the logistic function, but for now we'll call it the logistic function, but especially when we get to neural nets, we're going to tend to want to call it the sigmoid function instead. And the sigmoid function is a pretty famous function. So again, what I want to emphasize here is that we started by asking what are the posterior probabilities, and we wound up with this famous sigmoid function applied to the decision function that we're using to do classification. That's a pretty nice, elegant relationship once you get through all the math. And we should take a look at the logistic function so we can build a little bit of intuition for what's going on here. So here it is. That's the logistic function. So the horizontal axis, let's call that gamma, S of gamma. And the vertical axis is S applied to gamma, this logistic function or the sigmoid function. A few things worth knowing about it are, first of all, that at 0, it's exactly 1/2. In the limit, as S goes to infinity, its upper asymptote approaches 1, but never quite gets to 1, of course. Symmetrically, at the bottom left, this asymptote, when you go to negative infinity, in the limit, S approaches 0, but again, never truly reaches 0. And this function is monotonically increasing over its whole span from minus infinity to infinity. So we're converting our decision function into a posterior probability. And in particular, what S0 equals 1/2 means is that on the decision boundary, where the decision function is 0, we're saying there's a 50% chance of class C and a 50% chance of class D. That's basically what S0 equal 1/2 means, 50% chance of class C. Any questions about that? Yeah. Oh, do we have any assumption on how we estimate sigma? So the last part of this lecture will be on how we estimate sigma. We don't know yet. We're just assuming we can do it. But whether you use the biased estimator or the unbiased estimator to anticipate your question, you can use either one. The best way to decide which one works better is validation. There isn't really an a priori reason to believe that either the biased or the unbiased estimator of the variance is going to be better for machine learning specifically. You just try them both and see which one gives you better validation accuracy. Other questions? All right. Quadratic discriminant analysis was what naturally falls out of empirical risk minimization. When you know the distribution of your normally distributed classes, linear discriminant analysis can sort of be viewed as a special case of QDA where every class has the same variance or the same covariance matrix if you want to look ahead to next week. So LDA is going to give you always linear decision boundaries. You're never going to get curvy decision boundaries. And that's a side effect of the fact that we're assuming that every class has the same variance. One nice thing about that is because you always get a linear separator, a linear decision boundary, LDA is less likely to overfit than QDA is. There's just a less flexible decision boundary. So again, we get from QDA to LDA by adding one additional fundamental assumption. We retain the assumption that every class is normally distributed, but now we add the assumption that every Gaussian has the same variance. So sigma is the same for every class. And next week we'll do that with a covariance matrix instead of a scalar variance. So the nice thing about this assumption is that if sigma is the same for every class, then the equations simplify nicely Specifically, when you look at the decision function, QC minus QD, the quadratic term in QC cancels out the quadratic term in QD, and you're left with something that's linear. The quadratic parts just disappear. And so here's the linear part that's left over. So you can take the formula I gave you for QC and QD and check for yourself that this is correct. It's pretty simple. Again, the thing I want to spotlight is that x only appears here, and the whole formula is linear in x, not quadratic anymore. All right, so, but otherwise we do the same thing we did in QDA, it's just now that the function we're doing it with is linear. Another way to think about this, so the formulation I just gave you there is a two-class formulation. What if you have 5 classes? Do you have to compare every pair of classes? Like, do you have to do this for all possible values of C and D? No, you don't. What you do instead is you compute one discriminant function, one linear discriminant function for each class. And then you choose the class that maximizes those linear discriminant functions. And those functions are mu of C, mean of class C, dot inner product with test point x over sigma squared minus the squared norm of the mean over 2 sigma squared plus the logarithm of pi c. So again, the idea is like, let's say someone gives you the MNIST training set and says, here are 10 different digits. I want you to take in a new digit, x, and tell me which of those 10 digits it is. Well, what you'll do is you will have 10 of these. You will have a different mu c and a different pi c for every digit. And in fact, you will do that in homework 3. So this is not just abstract, it's going to be concrete. And so now you've got these 10 formulae. And someone gives you a test point x, you plug it into all 10 formulae, you pick which of the 10 is the biggest. Now, why does that work? Well, I sort of started with this, and I went to here. But in the 2-class example, I mean, you can see that this term for c is going here, this term for mu c squared is going here, and this term is going here. And then if I have the equivalent 3 terms for class D, then this term for class D is going here, this term for class D is going here, this term for class D is going here. So if I compute one of these for each class and then pick the biggest one, equivalent to if I did this comparison for all 45 pairs of classes and picked the best one. But I want to come back to the case where there's just 2 classes and say a couple more things about that. All right, so we're used to, at this point, when we have a linear decision boundary, we're used to expressing it in the form w dot x plus alpha equals 0. Are we doing that here? Why, yes, we are, because we can look at this here, and we can call that w dot x. It's just a vector times x. And we can look at this thing here. Don't forget the minus sign in front. That's important. And we can call that alpha, because that's just a bunch of constants added together. So this is in the form w dot x plus alpha, the classic form we use. So you can recognize that w is the normal vector, meaning this thing here, mu c minus mu d over sigma squared, is the normal vector. The other thing that happens then in the two-class case is that the posterior probability is, well, this is the definition of the posterior probability at a test point little x. And we can write that as the logistic function applied to w dot x plus alpha. So this simple standard linear decision function, you just plug it into S, and now you've got your posterior probability. So not only can you say, hey, I'm in class C, you can also say, there's a 72% chance I'm in class C. And if you want to think about what this will look like, well, go back to what the logistic function looks like here. And now just imagine scaling it and translating it. So maybe it's moving it to the left or the right. Or in a higher dimensional space, you might be moving it in other directions. But basically, this is just scaling and translation of x before applying the logistic function. So I want to show you where this is coming from here. So this graph here shows you the connection between the Gaussian distributions of the two different classes and the logistic function that you get. This is just in one dimension. So our feature is the x-axis. There's only one feature, x1. But we've got two curves here. We've got the class conditional distribution for C, and we've got the class distribution for class D. And this is the logistic function, S of the decision function, which is equal to, in this case, this is logistic for FD. I guess I should have labeled them the other way, but too late now. FD over FC plus FD. That's what the black curve is. So the relationship between the two, the red and the pink curve to the black curve, is that you take the pink curve, you divide it by the sum of the red and the pink curve, and you get the black curve. The black curve being the posterior probabilities, the red and pink curves being the original PDFs. Well, the posterior probabilities really, so the original PDFs multiplied by the priors. It's interesting to also see what this looks like when you go to a higher dimension. Here's an example where now I've got a two-dimensional feature space instead of just one dimension. And the basics are the same. Once again, we have the posterior probability for class C, the posterior probability for class D, and then the no, I'm sorry. This is the distribution of class C times the prior. This is the distribution of class D times the prior. And this here is the posterior probability of pink being the correct classification. So what I think is interesting about this graph, though, is that the red Gaussian and the pink Gaussian, they both look two-dimensional. They're nice and circular. But when you get the logistic curve in this higher dimensional space, it looks pretty much like the one logistic curve. It looks like I took this one-dimensional curve here and I just extruded it along the other dimensions. And the decision boundary on this thing is going to be the set of points where the posterior probability is 1/2. So that's right here. And that, of course, is a linear decision boundary, because that's what LDA produces. But the logistic function itself is not linear, but its isocontours, its isosurfaces, are always linear. Now, one more thing I want to show you is, now, okay, what will this look like if I have more than two classes? Well, LDA looks something like this. It's just a regular Voronoi diagram without the curvy edges. So this kind of looks like the previous Voronoi diagram, but now, since we're doing LDA, since we are assuming that every class has the same variance, that means we're only going to have linear boundaries between two different classes. So all of the curves have become straight lines in this image. But you still have lots of branching because we have multiple classes meeting each other at branch points. So this is just a regular Voronoi diagram, and the reason why it came out this way is because if you look at the widths of the isocontours of any one class, they're exactly the same as the widths of the isocontours of any other class, and that's what gives you straight line boundaries instead of curvy boundaries. Oh, I should say that you get this Voronoi diagram not only assumes that you're doing LDA, it also assumes that all the priors are equal for all the different classes. In that case, it's a true Voronoi diagram. So there's one more thing I want to point out about LDA now, which is if you have two classes and they both have the same prior probability, which means they both have to be 1/2, 50% chance any random sample point is in class C, 50% chance that any random sample point is in class D, then, well, let's plug that in to our decision function, and what we get is that the decision boundary is now mu C minus mu D dot x minus mu c minus mu d dot mu c plus mu d over 2, that's all equal to 0. So that's my decision boundary when the priors are equal and there's two classes. How did I get that? Well, what I did was I plugged those priors into this formula here, and then I did a little bit of, well, what happens when you do that is that the two priors cancel each other out. And then I just took whatever was left and brought it back down with a little bit of factoring here. A little bit of factoring there. And the reason why I want to show you this is because we've seen it before. I think in lecture 2 or 3, I forgot which one, I talked to you very briefly about the simplest of linear classifiers called the centroid method. Well, here it is popping up again. So when I originally introduced the centroid method, I pointed out that it has some flaws for some types of data, but if you really do have two different classes that are distributed with a normal distribution or something pretty close to a normal distribution, both with the same variance and both with the same prior probability, then the centroid method is actually a good idea that has a lot of statistical support for its success. But, you know, if the priors are not equal, if the variances are not equal, we now have a more general technique, QDA, which can adapt to whatever priors or variances you have. Any questions about that? Yeah. Oh, when you consider the posterior probability, no, we don't always assume that pi c equals pi d. So yeah, the posterior has to factor in pi c and pi d. In particular, this is where pi c and pi d get factored into the decision function, and then the posterior is just s, the logistic function, applied to that decision function. So that's where the prior probabilities enter the posterior. Other questions? Yeah. Where pi c is not equal to pi d? I think, if I remember right, that the original graph here, that the blue class and the red class there actually do have different prior probabilities. But I don't remember what they are, sorry. It's not always that easy to tell visually. But, I mean, what you have to do is you have to basically look at the two PDFs and look at the volume under each PDF. And if they're the same, then the prior probabilities are the same. This is, the PDF after it gets scaled by the prior probability. If they're still the same size, then they both had the same prior. If they now have different amounts of volume under the two scaled PDFs, then they have different priors. And that'll show up then when you look at where the decision boundary is. The next thing I want to talk about now is how do we estimate the parameters of the Gaussian distribution, and how do we estimate the prior probability for each class. So the rest of this lecture is the first part of the QDA algorithm. When you're getting started with QDA, the first thing you have to do is figure out what is a good Gaussian curve to approximate the distribution of points in class C, and what is a good Gaussian distribution to approximate the real distribution of points not in class C. Statisticians have a very famous technique for trying to estimate those quantities. It goes all the way back to 1912 and a statistician named Ronald Fisher. So what I'm going to do is I'm going to start by talking about how you estimate the prior probabilities for each class. That's going to be easier because it involves a discrete distribution. And then we're going to fit the Gaussians, which means for class C, we want to figure out what is the mean and what is the variance, well, the variance, yeah, of the distribution, assuming that we have normally distributed points in each class. So I'll start with pi c. And the way we're going to approach this is we're going to imagine we are flipping coins, but not normal coins that give you 50% chance of heads, 50% chance of tails. We're going to flip some biased coins. And so the coins we're flipping come up heads with probability p for some parameter p that we don't know yet. And then obviously come up tails with probability 1 over p, 1 minus p. All right, so suppose I'm flipping my coins and I do 10 coin flips. And suppose that 8 times it comes up heads, and the other 2 times it comes up tails. So the kind of weird question a statistician would ask is, what value of p is most likely to give you this outcome? All right, well, let's try to figure that out. All right, well, we know that the number of heads that you get is a random variable, we'll call x, that comes from a binomial distribution. I hope you remember a little bit about the binomial distribution from your previous probability class. The probability of getting little x heads exactly is n choose little x times p to the power of little x times 1 minus p to the power of n minus little x. So again, this is the probability of getting exactly x heads when you do n coin flips. In the example that we're working through right now, n is 10. And so little x is 8. The probability that we are going to get exactly 8 heads, well, if you work that out, it comes out to 45 times p to the 8th power times 1 minus p squared. Now again, I want to know what value of p is most likely to give me 8 heads, or in other words, what value of p makes this probability highest. So this probability, I'm going to call that the likelihood of getting a certain number of heads, 8 heads, given parameter p of my binomial distribution. So this is going to be the definition of the likelihood function. So again, you'll notice that the likelihood function is a function of the distribution parameters and nothing else. So when you do that, when you have this probability that's purely a function of the distribution parameters for a specific outcome, then we call that the likelihood function. Now, the very famous technique of maximum likelihood estimation which, that's a lot of syllables, so people usually just call it MLE. MLE is a method of estimating the parameters in a statistical distribution. By picking the parameters that maximize the likelihood. And by the way, I want to say that maximum likelihood estimation is just one technique in a broader class of techniques for what is called density estimation. It's not the only way to do density estimation, but it's certainly the most famous one. And so density estimation is the problem of figuring out what the PDF is or might be for a bunch of data someone gives you. So let me phrase this as an optimization problem, just because we like to phrase formal optimization problems in this class. We are trying to find the parameter p that maximizes this likelihood function L of p. That's our goal. Put it in a box to remind you that this is a formal optimization problem. And now we're going to solve it. But before we solve it, let's just look at this function that we're trying to maximize. In this case, it's really not a very complicated function. So if you look at this, can you see where the maximum value is? It's pretty easy. It's pretty obviously here. Drawing that down, well, we get about 0.8. Let's do a little calculus, though, just to formally verify it. Because that's what mathematicians like to do. So we're going to take the derivative of this likelihood function with respect to p and set it to 0. So, got to work on L's. So the derivative of the likelihood function with respect to p, it's not too hard to figure out that that is this and we're going to set that derivative to 0 because we're trying to find the maximum, and the maximum is a critical point. In this case, the function has only one critical point, which makes it really easy to get an answer. This simplifies to 4 times 1 minus p equals 0, from which it's pretty easy to figure out that the optimal p is 0.8. This is really not surprising. It should not seem surprising that a coin that is biased to come up heads 80% of the time is the coin that's most likely to produce 8 heads when you do 10 flips. But it's nice to have verified that in a good formal way of doing. All right, so, but the real question now is, what do coin flips have to do with estimating prior probabilities when you're doing a machine learning problem? And so let's suppose that coin flips are sample points, and the ones that are heads, that's class C. What we're really trying to do here is we're trying to estimate the prior probability of class C. What is that? Well, we're going to estimate that that is 0.8 in this case. If our data say we have 10 sample points and 8 of them are in class C, then we're going to guess that on average, if we poll a bunch of new test points, 80% of them will be in class C. Any questions about this? The function that we are looking at, that we're taking the derivative of, is this, where x is 8 and n is 10. So in that particular case, this is p to the 8, and this is 1 minus p squared. And so what's going to happen is we're going to use the chain rule, and that's going to wind up giving us two different terms, one where the 8 becomes a 7, and one where the 2 becomes a 1. So coming back to this, you can see indeed there is one term where the 8 has become a 7, and there's another term where the 2 has become a 1. Does that make sense? Okay. Yeah, got to do the chain rule carefully. Yes? That is true. We are assuming that there's no prior for P, right? And if we didn't assume that there's no prior for P, if we had a sort of prior for P, there is a very closely related technique called MAP, maximum a posteriori. Sorry, is it maximum a posteriori? Or it's been a while. Method that is also very well known by statisticians and can be used and often is used in machine learning, but it's beyond the scope of this lecture. Other questions? Before we go, I want to apply MLE to one more distribution. This is the one that's more important. What we just did was kind of a warm-up. The answer came out to be pretty easy and obvious. But what about fitting a Gaussian distribution to a bunch of sample points? How are we going to do that? So someone gives you a bunch of sample points, x1 through xn. For now, I'm assuming that these are all points in the same class. So we're just doing one class of n points now. And we want to fit a Gaussian distribution to those points. Problem with that is now we want a normal distribution instead of a binomial distribution, is what we did before. If I generate a random point from a normal distribution, what is the probability that that point will be exactly x1? Well, it's 0 because the normal distribution is a continuous distribution. If you generate a random point from a normal distribution, there is basically no chance that it's going to be exactly x1. So this is a little bit, this means that if I ask, what is the probability that if I generate n points, that I'll get these n points, that's also 0. So likelihood, the concept of likelihood, still exists, but it's not a probability anymore. we're just going to go ahead and do likelihood anyway, despite the fact that the likelihood is, in one sense, 0. So I'm going to say the likelihood of generating these points so here's a likelihood function. It's going to have two parameters, the mean and the variance of my distribution. And I'm going to use this notation where I have a semicolon and then I follow it up with all of the input points. That likelihood function is equal to, I'm going to make it the product of f of x1, f of x2, now, this is sort of like multiplying the probability of getting point x1 by the probability of getting point x2 by the probability of getting point x3 and so on, except that all those probabilities are 0, so I use the PDF instead. The PDF is not 0 at any of those points. It's strictly positive. And so I'm actually going to get a number, which you might ask how meaningful that number is, and I could talk more about that after class if you really want the details. But that number does give us some sense of whether this is a plausible set of points to get out of this distribution. And so now what I want to do is I want to choose the parameters, mu and sigma, that maximize L, just like I maximized L with the previous problem. One thing that makes this a little tricky is that when you multiply a bunch of things together, it's not quite so obvious how to optimize that. What we're going to do, though, is just take the logarithm of that, and that'll turn all those multiplications into additions, which makes optimizing a lot easier. So to maximize the likelihood, we're going to maximize something called the log likelihood, which is usually written little l with the same parameters. And that's just the natural logarithm of big L, the likelihood. And remember I told you earlier in this lecture that the logarithm is monotonically increasing for all positive numbers. Therefore, maximizing the likelihood is equivalent to maximizing the log likelihood. So what did I get out of this? Well, I get to rewrite my objective function in the following form. Now, instead of multiplying a bunch of things together, I'm going to take the log of f of x1 plus the log of f of x2 plus so on to the log of f of xn. And since those are additions, this is going to make maximization easier. Now, next thing I want to do is I want to actually substitute the normal PDF, well, the log of the normal PDF in for each and every one of these summons. And so that will become the sum over all n sample points of minus, here's the norm of xi minus mu squared. Mu is the mean of all these sample points, over 2 sigma squared minus d times the logarithm of root 2 pi minus d times the logarithm of sigma. Where did this come from? Again, this is just the natural logarithm of the normal PDF. All right, so now what I am looking for is I want to find the mu and sigma that maximize little l. To do that, I'm going to use calculus. And now I have to use partial derivatives because there's multiple parameters. There are all the parameters in mu, because mu is typically a vector. So I want to set the gradient of L with respect to mu to 0 to find a critical point in L. And the critical point I want also has to have the partial derivative with respect to sigma being 0. Question? Do we assume that all the features are independent? Well, the fact that we are using a scalar variance instead of a matrix, like a covariance matrix, is kind of implying that we believe that this data can be modeled without correlations. Come back next week for how to deal with correlations. All right, so what is the gradient of little l? It is that. All right, so set that to 0, because we're looking for a critical point of little l. And so if you solve that, setting that to 0, then you get this. Our estimate is that the mean of the distribution is the mean of the sample points, the sample mean. Not too surprising. If you probably know from your statistics class that if you generate enough points in a distribution, especially a normal distribution, the mean of the sample points is a good approximation to the mean of the actual distribution. Having said that, though, this is not the mean of the actual distribution. It's just an estimate. So we're going to put a little hat over it, which is how statisticians say, this is an estimate of a true parameter mu that I cannot know. And now we're going to also set the partial derivative with respect to sigma to 0, and that's going to tell us the correct value of sigma. So if you do the calculus, then the partial with respect to sigma is this. So I set that to 0, and if you do a little bit of work to solve for sigma squared, you could solve for sigma, but it's easier just to get sigma squared. You will get this expression here. And this expression is, well, we're trying to approximate the variance of the distribution, but this isn't the exact variance of the distribution, which we cannot know from a finite number of sample points. So I'm going to put a hat on top of that to say this is an estimate of the variance of the distribution. There's one more problem, though. To compute that estimate, I need to know the mean of the distribution. But I just told you that we cannot know the mean of the distribution. So instead, we have to settle for our estimate and use mu hat instead of mu when we're computing sigma hat. All right, so you might notice that this thing is essentially what's known as the sample variance. So another way of saying what maximum likelihood estimation gives us is that we should use the sample